This video is going to walk through an online simulation that normally I take a whole day in class, giving you guys time to play with. But because it uses Java, I can't really assign it because you can't do it on your iPad, and I don't really know if you have technology. This simulation is an introduction to the idea of reaction rates. What affects the rate at which a chemical reaction happens? So this unit is about reaction rates and equilibrium. So this first little simulation here, essentially I have a reaction, A plus B gray, and then when the reaction happens, I make AB, so B comes in bonds with A, and then C, oh, this little gray ball C is by itself. So how the simulation works is if I pull this knob back, I put some amount of energy in, okay, and that's the amount of energy I'm putting into the yellow ball. So if I put this amount of energy in, right, total energy that's below all the rest of this, it goes and it hits, but you can see that no reaction's happening because up here on the separation view, you're not making product, right? They're hitting, but that's about it, okay? So we would say that whatever the scenario is, this was an unsuccessful reaction. These reactants, while they can come together to make a product, didn't. So to show you what it looks like when there is a successful reaction, if I pull this back with more energy and let it fly, you'll see now product is made. So every time they hit, they do go back and forth because this is a reversible reaction, but you can see that this is a successful reaction. So if you start to consider this, this unit is about reaction rates and equilibrium. In order to make a reaction go faster, we have to understand what makes a reaction happen in the first place. So if we look at the simulation, we can see step one, the reaction is only happening when they hit. So like right now in the simulation, they have enough energy to make a reaction happen, but they can't happen unless they come in contact. Now, just then they came in contact and it was not a successful reaction. So it seems like we have a couple different variables that allows for a successful reaction to happen. Step one, they have to hit. Step two, they have to hit with enough energy. And then step three, there's something about this orientation. So if they just hit like willy-nilly, you don't make a reaction happen. Okay? So again, to show you, if I put in less energy than I did before, so less than the peak, when they hit, no reaction is going to happen. Even though they're hitting and they're hitting with the appropriate orientation, nothing happens. But let me show you, if I put in tons of energy, but hit it at an angle, now I have plenty of reaction or energy for the reaction to happen, but because they're not coming in contact, it's not happening. Now again, when they did come in contact, because the orientation wasn't appropriate, the reaction didn't happen either. So when we think about reaction rate, we have to understand why a reaction would happen in the first place to understand reaction rate. So if we set up this reaction with just some of each reactant and very low energy again and let it fly, you can see over here on the right-hand side that some of the reactants are hitting and making successful collisions. So already when I put 10 in of each, one has become product. If I asked you to try to speed up the rate at which this reaction was happening, there's a couple different variables we could try. Okay? So what would happen if I heat it up? If I heat up the reaction, would I have more successful collisions or less successful collisions? Okay, so we watch them again, still only getting that 9 of 1, raise the temp a whole lot. And let's see what happens. Okay, now we're having successful reactions. So heating it up is causing a faster reaction rate than the one I had before. Another option of something we could affect to see what happens to the reaction rate is what if I put more in? So instead of just 10 of each reactant, I put in 50 of each, okay? They're still at really low energy. So the question is, do I have more reactions happening? And it looks like I do, right? So about 1/10 of them was reacting before, and now I have 9 out of, almost 10 out of 50. So that is more than just the 1/10 that was happening. So far, increasing the temperature caused the reaction to occur more rapidly, and also increasing the amount of reactants. So that's a couple things this reaction shows. The other thing that does show, since this is a new concept for us, is a reversible reaction. Okay, so right now in the simulation, we're seeing a reversible reaction. You know it's reversible because if you watch the counts over here on this right-hand side, we'll see my reactants becoming products, like now it's 41 and 9. But we'll also see as they hit, if they hit with the successful collisions, you'll see a reverse, like it's become 40 and 10, 39 and 12, 38 and 12, 39, 11. It's oscillating here, right? So I'm making product. My products are also going back to reactants. Now, I changed the simulation slightly just to show you that this idea of equilibrium, again, eventually you get to this point where it's kind of stopping or the numbers aren't changing. So the way this is different than a forward reaction is that technically it never really stops, right? My numbers are continually changing, kind of up, down, like oscillating, reactants to products, products to reactants. But I've reached this point of equilibrium, the point at which great changes aren't happening, just slight variations. So it's different than a normal forward-facing reaction because the reaction doesn't stop. Now, there are two thinkers in terms of questions I like to look at in relation to this particular simulation that I want you guys to consider. So going back to our first screen that we had here, in order to have a successful reaction, if you look at the energy on the right-hand side, what I can tell you is if I put any energy in that is below the peak, so if I'm just below the peak, no matter what I do, they cannot hit to make a product. Okay? If, on the other hand, I am at the peak or any amount above the peak, products can form. Now, if you compare that to this simulation here, where I'm going to right now put my average energy below the peak. When I put substance in, though, at below the peak, reaction does occur. So right away, I have reactants becoming products. My question to you is why? The main thing to think about in relation to these two different screens is on this screen, my green line right here corresponds to the total average energy of all the particles in the system. Where in here, with the fact that I only had one atom or one set of atoms, the total energy was of all of these, right? So that is a difference here. But if you look, my question is, why are successful collisions happening here when I'm below energy, where if I go over here and go below energy, no successful collisions are ever possible? Okay, so that's one question I ask you to consider. The other one that I like to ask, if I put in 30 and 30 and let them fly and watch these numbers, we see it going 29, 28, 27, 26, you know, slowly changing, 25, 24, 22, right? They're progressively changing. And if I put a lot in, they might change rapidly, but it's not instantaneous. It's not like the minute I let this reaction start, it went from 30 to 19, right? It was slower than that. And the question is why? Why aren't reactions instantaneous? Why do some reactions take time? Given the fact, again, that in order for reaction to happen, we have to see what we saw in this first slide. Okay, so in order for a reaction to happen, we have to have this energy and this collision and this angle idea. So why isn't it instantaneous over here? Why didn't I just go straight from 30 to 20? So those are the main things I want you to consider. Have a nice night.